Welcome back, my Algebra 1 students. We are in Lesson 61. We're going to talk about sets and subsets. We discussed sets earlier, and let's say we had a set here, and the members of this set were 1, 2, 3, and 4. Right? I could say, with this symbol here, that 4 is a member of set R. This little symbol right here, actually, I'm going to use another pen to illustrate that. This little symbol right here means is a member of. All right? By the same token, I could say that 5 is not a member of R. This symbol right here means is not a member of whatever the set is that's listed. All right, what if we have two sets? And let's say we have set B, and within set B, we have two numbers, 2 and 4. We can say that the members of set B are also members of R, but how do we do that? We call this a subset, and a subset is any set of items or numbers that are duplicates all contained within another set. So I could say that B is a subset of R. So this little symbol right here means is a subset of. And all subset means is all members are in another set. That's all that means. Okay? So what do we know about our number system? Well, we know that we have this big umbrella, right, that is real numbers. We have real numbers. And within real numbers, we have two groups. We have, here's our two groups. We have irrational, I think there's two R's there, irrational, and we have rational, right? So irrational numbers are, those are the definition that would be that is really bad handwriting. So non-terminating and non-repeating decimal numbers. Those are irrational numbers. Those are numbers we just can't wrap our head around, and it makes doing mathematics difficult. It makes calculating them really hard because they don't ever end, right? And they don't repeat, so there's not a pattern that we can calculate out. So those are irrational numbers. Rational numbers are everything else. So rational numbers would also include terminating or repeating decimals, right? It would also include integers. Integers include whole numbers and whole numbers include natural numbers. So we could actually say that irrational numbers are a subset of the real number system. We could say that rational numbers are a subset of the real number system as well, because we have these two categories that fall under real. Real includes both of them. Now we could say that, let's just skip to integers. Integers are a subset of rational numbers. Then we could say that whole numbers are a subset of integers. And if you don't remember what integers are, they're all the negative whole numbers and all of the positive whole numbers and 0. And we know that whole numbers are 0 and all the positive numbers. And we know that natural numbers, those are the numbers we count with, that starts at 1. So whole numbers are the natural numbers plus 0. So the whole numbers have more than the natural number does. So the natural numbers are a subset of the whole numbers. Now we could also say that integers are a subset of real, whole numbers are a subset of real, and natural numbers are a whole set of real, because all of these fall under rational, right? Whole could be a part of rational, natural could be part of rational. All of those are true because they all fall under this real category. In fact, you can write it the long way by saying that natural numbers are a subset of whole numbers, which are a subset of integers, which are a subset of rational numbers, which are a subset of the real number system. Okay, so this is smaller than this is smaller than this is smaller than this, and this is smaller than this. And everything in this one is included in this one. This one has more. Everything in this one is included in this one. Everything in this one is included in this one. And everything in this one is included in this one. So I hope that that clears up what this means. This little symbol is a member of. All right, and that you can see how the number system works as a result or in relationship to those symbols. All right, I want to talk to you about one more thing in this lesson, and then I'll let you go. How to answer correctly in algebra. In pre-algebra, we learned how to go from this to this, back to this, right? We learned how to flip and flop and what those numbers mean. We learned how to evaluate those numbers. In elementary math, we learned that this was the correct answer, that this was the final answer, that this was a division problem, and that you wanted to simplify it and tell how many whole parts you had. Okay, in algebra, we don't do that. In algebra, we prefer improper fractions versus mixed numbers. I don't want to see a mixed number in your work anywhere, ever. That is incorrect in algebra. The other thing that is incorrect in algebra that you don't want to do, I don't ever want to see that. The only time that is okay in algebra is when you are dealing with money. Money, it's okay. In algebra, we don't like mixed numbers. We don't like decimals. Now, sometimes you are given problems that contain decimals, like for instance, 0.4 plus 0.02x equals, 0.0, let's say 42, right? Sometimes you're given a problem with decimals in it. You're given a problem with decimals so that you can learn how to get rid of the decimals. And the way we would get rid of this decimal is by multiplying everything by 1, 2, 3 decimal places, or 1,000. So we would multiply all of this by the largest number of decimal places would be the number of zeros that you have. And that would be moving the decimal place back 3. So 1, 2, 3 would be 400 plus 20. 1, 2, 3 equals 42. That would be how you would solve that problem. The whole point of the decimal is to teach you how to get rid of the decimal. That's why we give you those problems. All right, we don't like decimals. We don't like mixed numbers. The reason we like improper fractions, let's say we have a number here. We have 42 over 49. And we are multiplying that by 3/7. And we're going to multiply that by 7 over 2. We're not actually going to multiply that. That's not what we do. That's not the point. What we do, the reason we like an improper fraction, 7 over 2, so we can factor. We want to be able to factor things out. We can't do that if we put it in a mixed number. We can't do that if we put it in a decimal. But what we can do is we can say, this 42 is 6 times 7, right? We know when we multiply fractions that we're just going to go straight across. So we do this. And then this is 7 times 7, right? We also know that 6, let me erase this, it's 2 times 3, right? So we can cancel. We can get rid of stuff. Here's a 7, we can get rid of that, and get rid of that. We can get rid of this, we can get rid of this. We can get rid of this one, and we can get rid of this one. And that leaves us with an answer of 9 over 7. Because 3 times 3 is on top and 7 is on the bottom. The way that we learned in elementary, or the way that we learned in pre-algebra, was to multiply all of these out and then reduce them. That is the hard way. That's the long way. And if you were to simplify this into 5.5, or what would this be, 3.5, you can't do that. You can't do that with a mixed number. You have to have an improper fraction in order to factor both of these out. Because you see, we completely eliminated this entire fraction by leaving it as an improper fraction. So that is why we prefer in algebra, leave it as a fraction. The only exception to leaving it as a fraction is if you have a number like this. If you can reduce this to a whole number, do it. If you have a number like this and you can reduce it to a smaller fraction, do it. Those are the only times that you would adjust a fraction. If you have an improper fraction that can be evenly divided into a whole number, that is when you do it. If this was 13 over 2, you would leave it 13 over 2. You would not turn it into a mixed number. Okay, be thinking about that whenever you answer problems in the future. Be thinking about, oh, well, this is not evenly divisible. It's got to stay the way it is. Or, oh, these are both even. They can be reduced. Let me reduce them. And the way that you reduce a fraction, yes, you can divide both of these by 4 and get 1/2, but it is easier to factor. It is so much easier. You can look at this one and you can tell, right? You could tell right away that this is 1/2. But there's a way to get there if it's not so obvious, right? If it's not so obvious, let's say you have 72 over 144. That's not immediately obvious that's 1/2. But what you can do is you can say, okay, 72. All right, I know that is going to be 8 times 9. And 8 is 2 times 4, which is 2 times 2. And 9 is 3 times 3, right? 144, that's 12 times 12. So 12 is 2 times 6, which is 2 times 3. So that's 12. So I need to do that again because it's 12 times 12. Now I can get rid of that one I can get rid of that one. I can get rid of that one, and I can get rid of that one, and then I can get rid of that one. Oh, when you get rid of all the factors on the top, you'll always have a 1 left behind because anything times 1 is still the same. So if you get rid of all of your factors, you just put a 1 up there. Guess what? You have a 1 over a 2 left behind. So that's your answer. And you got there not by taking 72 and dividing it and dividing it and dividing it and dividing it. You just factored it out, eliminate everything that was the same, and whatever's left is your answer. Just like we did over here. But if it's obvious, it's 4 over 8, you know, okay, 8 is 2 times 4. That's 1 times 4, 1 over 2. Duh. All right, so I'm going to let you go with that, and I'll see you in lesson 62.